I'm Jeffrey Hazboun. I'm a physicist. Let's answer some questions off the internet. This is physics support. At Pizzazz91 asks, how do black holes influence the space-time around them? Anything that's massive will bend space-time. So if I think about this sheet of elastic as being space-time with nothing in it, as soon as I put something that has any mass in there, it bends space-time around it. If I then take something really small like this marble and give it a little bit of oomph, it'll orbit around that object. And it's that following curved space-time is why the Earth moves around the sun. So if I have a really big object, and I look at what that looks like in space-time, that bends it even more. The key with a black hole is making something that's really, really dense. And as I increase that density, that stretches this space-time further and further and further down so much that light can't escape that curvature anymore. And that's what we call a black hole. At Pedals for Jack asks, wait, what's space-time? Space-time is the thing that we live in. It is 4 dimensions, 3 dimensions of space, and adding to that the dimension of time. It's what we're moving through as we sit still. It's what we're moving through as we walk through our house. At Frivinky Smacks asks, how do you split an atom? What you're really doing is you're splitting the nucleus. And let's say this is the nucleus of a uranium atom. And what you do is you shoot another particle at it, usually a neutron, really, really fast. And when you shoot it at the nucleus breaks into pieces, into a few different pieces that are smaller nuclei. And when you do that, it also, as you can see, releases a lot of energy. And that's where the first nuclear bombs came from, and that's where the energy we get from nuclear power comes from. User Alir8203 asks, if the sun just suddenly disappeared, it would take us 8 minutes to find out. But does Earth still orbit where the sun was, or will it go out of the orbit immediately after it disappeared? The answer is it's gonna keep moving around the sun for another 8 minutes. We don't know here on Earth that the sun disappeared because it takes 8 minutes for the light to get to us from the sun. It also takes 8 minutes for any changes in gravity to get from the sun to us. At Mike Bianchi asks, hasn't read a goddamn thing about physics since high school. Hey, did you hear about the gravitational waves? I have heard about the gravitational waves, and I helped publish some of the recent results about gravitational waves. In case you haven't been paying attention, gravitational waves are these expansions and contractions of space-time that are traveling through space-time at us from supermassive black holes at the centers of faraway galaxies. One of the really neat things about gravitational waves is they pass unimpeded through the universe. We can actually get closer to the Big Bang using observations of gravitational waves. So they're gonna teach us all kinds of neat stuff about the early universe. At Only166 asks, one question, how do you detect gravitational waves in space-time? The first way we detected gravitational waves a few years ago was using lasers in big vacuum tubes. And you split a laser, you shoot it down 2 tubes, and you keep track of how far apart the mirrors are using the lasers to tell you the distance between the mirrors. That's called LIGO. The second way that we've learned to detect gravitational waves is by using these exotic stars called pulsars. They are really fast spinning stars that pulse every time they come into our line of sight. We watch those pulses over time. If the pulses arrive a little bit later or a little bit earlier, we can attribute that to the expansion and contraction of space-time between us and those stars. I'm part of a collaboration that looks at almost 70 of these stars in all different directions, and we've been monitoring it for almost 20 years. At the Tarek Hatib asks, I'm genuinely paying you $1,000 if you answer this right. Is light a wave or a particle? The answer is that light is both a wave and a particle. We've known the wave-like properties of light for a long time. There's a classic experiment called the Young's double slit experiment. Let's show it to you right now. Let's take down the lights. We're gonna take a laser pointer here, which is not how the original experiment was done. I'm just gonna take this plate that has a little tiny slit in it and point the laser through it. And what happens is it splits the light into 2 different waves. And those waves are a little separated from each other. They're not quite matched up because 2 different waves are meeting up with each other, and this is what we call interfering. And that's what gives us that pattern. There's actually 2 waves hitting there, and they're constructively interfering. So the black spots are actually actually the same as what you get in noise-canceling headphones. One of the waves is canceling out the other wave, and only a wave behaves like this. Lights, please. Light is actually something bigger than a wave or a particle. It's something we call a quantum field, and that quantum field has particle-like characteristics and wave-like characteristics, and we can measure both. So I think you owe me $1,000, dude. At Dr. ZGC Disney asks, what's the difference between fission and fusion anyway? Do you want to go fission with me? I don't want to be anywhere near where fission is happening. Fission is where you take a nucleus that's really big of an atom and you break it into pieces. Fusion is where you take pieces of atoms and you push them together to make something bigger. Fusion is what happens in the sun, where really small nuclei come together. And that is a huge explosion. And we've been trying to build something like that on Earth to make energy. We haven't been able to figure out how to control it yet. Shivanshu21212 asks, how will the universe end? The universe will end in the heat death of the universe, which just means that over time, the universe is expanding and all of the light that we know about is going to get degraded and absorbed by black holes. It just gets really cold and really dark. We won't be able to see anything in the distance and just nothing. The heat death of the universe is not something to worry about because it's going to happen 40 to 50 billion years in the future, and we're only about 14 billion years from the beginning of the universe. At Clown Prince Charlie asks, wait, are black holes / wormholes actually spheres? Watching Interstellar. Black holes are pretty much perfect spheres. If they're spinning, they are a little bit more expanded around their equator where they're spinning than at their poles, but pretty much spheres. So in that classic image from Interstellar, you see this pretty much spherical black hole at the center, and then you see all of this light, which is the light from the other side of the black hole getting bent around it. And that disk that you see across the front, that tells you that the black hole's actually spinning. And every black hole that we know of is spinning, like every other star in the universe. At 52xmax asks, what's so special about special relativity? Well, that's relative. Einstein, probably. Special relativity is special for a few reasons. Number one, it gives us a universal speed limit, which is the speed of light. Nothing can go faster than the speed of light. And that's unique to Einstein. He figured this out in 1905, and no one had really thought that there was any kind of universal speed limit. A couple other things that are really special about special relativity are that it tells you if you're moving close to the speed of light, time dilates. It gets longer. So if you're moving really fast, you experience time more slowly than someone who's not moving really fast. At Cowboy Vard asks, can someone explain the twin paradox to me in simple terms? You have two twins, both on Earth. One of the twins decides to be an astronaut. She takes off in a spaceship going super fast, almost the speed of light. It takes her 50 years to go out to a star and come back. When the astronaut comes back, the twin that remained, she's 50 years older. The other twin might only be 20 years old, depending on how fast she was going. And so it's the person in the rocket that will see time move more slowly and will only age 20 years. At Arez Force 1 asks, the speed of light as constant is falsehood. What's the speed of light in water? Slower? The speed of light as a constant is not a falsehood. We have a glass of water, and I'm gonna put this pencil in there. And when I put the pencil in, the pencil looks bent. The light that's coming out that you're seeing is bent. And that bending comes from the fact that as the light hits it at some angle, it sort of veers in that direction. The light's interacting with the water. It's getting absorbed and re-emitted. It's seeing a little bit longer paths as it gets scattered. And it's that makes the light look like it's bent. But those interactions take a little bit of time. And that's why we say that it's effectively moving more slowly. Between one interaction and the next, the speed of light is the speed of light. At Aquarius Donkek asks, the question is, how does time dilation work? Long story short, time dilation is the fact that when you're moving really close to the speed of light, time passes more slowly. It's pretty simple to write down. The time that passes for someone who's moving at some speed is proportional to how time is passing for someone who's not moving at that speed. And there's this funky square root down here. And what matters is the comparison of how fast that person's moving, that's what v is, as compared to the speed of light. And in that line there, And as you go faster and faster and faster, that factor of delta t prime gets longer and longer and longer, so time is passing more and more slowly. When you get to the speed of light, time no longer passes. At Neil Cameron 78 asks, are black holes really wormholes, or are wormholes really black holes? Hashtag science. We know black holes exist. We can see evidence for them out there. We've seen light around these black holes and what it looks like. We've seen the silhouette of a black hole. Wormholes are a shortcut through space-time from one place to another. The first idea of a wormhole is something called an Einstein-Rosen bridge. It would take moving faster than the speed of light to travel through. And we have no evidence whatsoever that wormholes exist. Some physicists have posited that if we use some of the special characteristics of quantum field theory, that maybe we can create tiny, tiny little wormholes that we can send a signal through from one place in space-time to another. And while these have been successful as thought experiments and successful as computer simulations, it's not yet been seen in the real world in a real-life experiment. At Matt P 1949 asks, you think time travel is possible under current physics understanding? No, probably not. At least not from what we understand right now. There's a couple of ways to think about how we might travel in time. One way is using a wormhole. Some physicists have done this thought experiment and written down all of the pieces you would need. So you build a wormhole that somehow changes and tunnels through space-time back into the past. You write down the math for what that wormhole looks like. The kind of matter that you would need to hold that wormhole open doesn't exist in our current understanding of physics. The type of matter that you would need to hold a wormhole open is called exotic matter. Things like negative energy density, which what does that mean? It means like thinking of something with negative mass. So I don't know if we're going to be building a time machine anytime soon unless we can figure out how to find and make this exotic matter. Brad Alexandru asks, is there anything infinite in the real world, or is infinity just a concept in our mind? Infinity is not just a concept in our minds. The most important infinity that I study is that the universe is infinite. So that's a great example of something that's infinite. We use infinities all the time when we're making predictions in physics, and it turns out that the size of the universe is infinite. The amount of time the universe will be around is also infinite. At One Day Well Be Okay asks, quick question, does anybody know the difference between particle physics and quantum physics, please? Particle physics is a small part of quantum physics, and quantum physics is the area of physics that really studies small stuff and the interactions on really, really small scales. But particle physics focuses on the particles that make up atoms, the fundamental particles that make up everything around us. At Cypher707 asks, I thought quantum physics was a fanfic. Absolutely not. Quantum physics is how the world works, but you have to look at a really small scale to understand what's going on. If I throw a ball up in the air, it comes down back into my hand. That's classical physics. Quantum physics acts in surprising ways. So instead of having pure predictions about what's going to happen at a quantum level, we just get probabilities. There's a 50% chance that this thing is going to happen, a 20% chance that this other thing is going to happen. If you watch a lot of Marvel movies, I could see why you'd think it was fanfic, because it gets used anytime you don't know how to explain the science that you want to do. At Ravenbiter asks, lecturer just asked what Heisenberg contributed to physics, and loads of people answered crystal meth. That's a different Heisenberg. The Heisenberg that we know is a very famous quantum physicist. He worked with the German government during World War II, but he's really well known for being one of the people who figured out all of these rules of quantum mechanics really early on. He came up with something called the uncertainty principle. Basically, if I know one aspect of a particle, like where it is, I can't know how fast it's moving very well. Or if I know how fast it's moving, I can't know where it is. At Tim Amberie asks, I just learned about quantum entanglement and I'm shook. How can two particles be so connected that they affect each other even when they're light years apart? Is this the secret to long distance relationships? Hashtag quantum love. Two particles light years apart can absolutely be connected if we've set them up in an entangled state. And what that means is we take two particles where the measurement has something to do with chance. So if I roll this dice, whatever value I get on that face, I'm gonna get the same value on the other dice, if that's how I've set up the entangled system. And these two particles can be very, very far apart from each other. And this is just how nature works. The weird part about this is the chance that no matter how I roll the dice, whatever it lands on, the other dice will land on the same exact value. This is just a fundamental way about how the universe works. At UTB asks, what the hell does the Large Hadron Collider do anyways? The Large Hadron Collider is the largest particle accelerator in the world. It is a huge 10-kilometer circle in Switzerland where we take two streams of protons. Protons are a kind of hadron. Hadrons are really heavy particles. Takes those two streams of protons and aligns them just right. They're going almost the speed of light, not quite, but almost the speed of light, and smashes them into each other. The faster you can get those protons to go, the more stuff comes out of that explosion when you smash them together. We're making new particles that we haven't seen before. They're part of nature, but they take so much energy to make that they haven't been around since the Big Bang when the universe was really tiny and really, really energetic. So not only are we learning about these fundamental forces, we're also learning about physics right at the beginning of our universe. At Physics in History asks, is string theory really a dead end? No. It's not a dead end. String theory is a theory that says instead of the fundamental pieces of the universe being particles, they're strings. And these strings can vibrate in different ways. You can have strings that are long, you can have strings that are in loops. And not only does it describe all of particle physics and quantum mechanics, some pieces of this actually predict what quantum gravity would look like. Gravity on a really small scale, which is not a theory that we have right now. So those are all the questions for today. Thanks for such insightful questions. Thanks for watching Physics Support.